In this video, we're going to look at the efficiencies of some of our existing methods in our two bag classes and our two list classes. So we'll look at ArrayBag, LinkedBag, AList, and LList. And we're not going to look at all the methods. We're just going to look at the add and remove methods and also the contains method. So if we look at the add method, this is the ArrayBag class. Remember, a bag is an unordered collection of objects, and the ArrayBag class implements that bag using an array. When we look at the add method and we think about the efficiency of this method, essentially what we're doing is we have some statements here. I'm going to ignore the check initialization method for this example. We have some just simple assignment statements. Is array full? If we look at that method, is just a simple comparison assignment statement. And then if we want to add something, we made the decision in our array-based implementation to add elements at the end of the array. So we have just a simple assignment statement and an increase here. So this add that adds an element to the end of our array to add it into our bag is going to run in constant time. This does not depend on the size of the array, right? We're not using a resizable array here. Once the array is full, we're not adding anything else. So you don't have to worry about copying entries over into a new array. That would change the efficiency. But for our non-resizable array, this is going to run in constant time. So this is even better than linear. This is constant. This is kind of as good as we can hope for, the add method in our ArrayBag class. Now again, remember that our resizable array class was a little bit different, and the add method in that class, if the array was full, we had to double the capacity of our array. So if we look at the double capacity method, that involves the copying of one array into another. And if you think about that, that is going to be less efficient. That's going to be linear runtime, right? Because we're going to need to go through our entire array to copy it into a new, bigger array. And so that's going to be dependent, the runtime of that is going to be dependent on the size of the array. So our add method for ArrayBag is going to be constant, but our add method for resizable ArrayBag, in the worst case, is going to be linear, not constant. Now, it's not going to be linear every time, right? It's only going to be linear the time you invoke it when the array is full. So on average, the efficiency is not going to be as bad as it might seem on the worst case. But let's go back to ArrayBag. So again, the add method here runs in constant time. So that's great. If we scroll down to the contains method looks like it's pretty simple, right? It just has these two method calls here. But this one here calls the getIndexOf, which is that private helper method. So let's take a look at that method and see what it looks like. The getIndexOf method has a loop here, and that loop is dependent on the number of entries in the array. So that's basically dependent on our problem size. That's what our n would be, essentially, is number of entries. And what we do is we loop over all the entries, looking at each one that is stored in the array to see if it compares, if it matches the one we're looking for, and then we return the index when we find it. Now this loop is going to be dependent on our problem size, right? Because if we have 10 things in our bag, this loop is going to take a certain amount of time to look at those 10 things. And if we have 100 elements in our bag, the loop's going to take longer. So the getIndexOf method is linear. It's order n, right? Because again, it loops through the entire bag, or the entire array. Now, we might not loop through the entire array. If we find the entry, let's say the one we're looking for is in the very first position of the array, we're going to find it right away, and we're not going to have to look through the entire array. But remember, when we talk about running time, we think about the worst case. We're always talking about the worst case. So the worst case is I'm going to look through my entire array, and it's going to be in the very last index, or it's not going to be in there at all. And that's going to be the worst case. So that's what we base our running time on. So the getIndexOf method is order n. So when we look back at our contains method, even though it looks pretty simple, it invokes a method that's order n, and that makes the contains method also order n. So any method that invokes getIndexOf is going to be order n, at least. Looking at our remove method, for our remove method here, we call the getIndexOf method. So again, that's going to be order n. And then we also call our private helper method remove entry. If we look at that method, the remove entry method doesn't have any loops. It just has a couple of statements where we are changing up the positioning of some items and decrementing our count. So these are all kind of constant time statements. So the remove entry is constant time. This is going to be order 1. So if we go back to our remove method, this call here is order n, followed by a call to order 1. So this would be, if we were writing out the running time, it would be something like something on the order of n plus something on the order of 1, but we know that it matters what the higher order term is, so this whole method is going to be on order n. Again, and that's because we invoke that get index of. Okay, so those are kind of some of the basic methods some of the core methods rather in the ArrayBag class. And adding, pretty efficient, order 1, but removing is order n, if we're removing the one where we send in a particular element. If we look at the other remove method, the one where we're just removing any old element from the array, or from the bag rather, here we don't need the get index of because we're not looking for a particular element. We're just going to remove any old entry, and we made the decision to remove the last entry. That remove entry method, remember, is order 1. It's constant. So this remove method is going to be O of 1. This is going to be a constant running time. So if we're just removing any old thing from the bag, it's pretty efficient. If we're removing a specific item from the bag, it's going to be order n instead of constant time. But either way, these are all linear algorithms and not quadratic. They're not n squared, so that's pretty good. Constant is great, linear is good. So this is a pretty efficient class. Again, because really bag is a pretty simple data structure. There's not a lot going on because the elements are unordered. So let's look at our other implementation of bag, the LinkedBag. And here we'll look at the add method. So here, adding a new item into our bag. We have some statements where we're creating a node. This is an assignment statement of the next variable, an assignment statement for first node, and an increment statement. These are all constant time statements. There's no looping here. This is not dependent on the number. None of these statements are dependent on the number of nodes we have in our chain. Doesn't matter if we are adding to an empty chain. This is going to take the same amount of time as if we are adding to a chain with 100 elements in it. It doesn't matter. So this add method is also constant time, just like our array-based implementation one was. So this is going to be O of 1. If we take a look at our contains method, for our contains method, here we have a loop, and here we are looping over the entire length of the chain. So here, how many times this loop is going to run is dependent on how many items we have in our chain. So again, that's going to be order of n. This is going to be a linear running time. Now we might get lucky and find the element we're looking for at the second one in the chain, but in the worst case, we're going to have to look through the entire chain and get all the way to the end and find it in the last position or not find it at all. And so it's that worst case running time that we consider for O of n. So this contains method, just like the array-based one, is going to be order of n, because essentially we have to look through the entire collection. We have our get reference to, which is a private method, which I'll come back to in a moment. So here's we have, again, our two versions of remove. In this version of remove, where we're just taking any old thing off the bag, here we have an assignment statement, a conditional, another assignment, a decrement, and a return statement. So again, all of these are constant time statements. These will all take 1 unit of time. So this remove method is O of 1, just like it was in the array version. If we're just removing any old item from the bag, we can do it in constant time. If we look at the other remove method, where we are removing a specific entry, here we invoke the get reference to method. So let's go up and look at get reference to. In get reference to, we have, again, a loop where we're looking through the chain because we're looking for the node reference that matches a particular piece of data. So here we, again, have to look through the whole chain in the worst case to find that node reference. So this private helper method is O of n. So this remove method that invokes get reference to is also going to be O of n. Okay, so similar, the two implementations, the array-based implementation and the linked implementation, have similar complexities of their add and remove methods. The add method is very efficient. It's constant time. The remove method, where we're just removing an unspecified item, is also constant time. And the remove method, where we remove a specified element, is linear time. And again, linear is pretty good. We're not going to complain about linear running time, but constant, of course, is best. Both of these classes are very efficient, again, because the interface is so simple. The data structure itself is so simple. So let's switch over to talking about the list classes. So let's look first at AList, which is our list implementation using an array. And remember, a list is an ordered set of items. So that's a little bit more of a complex data structure. So we might anticipate that our running times aren't going to be able to be as quick because we've got more going on with this class. So in our add method here, Well, our first add method just invokes our second add method. So we can just take a look at our second add method, where we send in a position and an element to add at that position. So we've got a conditional, another conditional, and then we have the invoking of the private helper method, make room. So let's go take a look at make room. The make room method has a loop, and this loop is dependent on the size of the array. So in the worst case, we'd be making room at the very beginning of our array, let's say in position 1, and we would need to shift everything else in the array. So this loop is going to be dependent on the size of our array or the size of our list. So this is going to be order n. This private helper method is going to be order n, because again, in the worst case, we are having to shift every single element in our list down one position to make room to put something at the beginning of our list. So in the worst case, this is going to run through that many times, however many elements we have in our list, and so that makes this whole method order of n. So if we go back to our add method, which invokes this method, we invoke that, that's order n. The rest of these statements look pretty, they're constant time. Let's double check ensure capacity. Ensure capacity makes sure we have enough room, and if we don't, it does copy the list. So ensure capacity in the worst case is also going to be order n. Now, are these two order n's that we're calling, are they looped together? Or I'm sorry, are they nested together? No, they're not, right? So make room will run and execute and finish before ensure capacity will run, execute, and finish. So this one might be O of n, and this one might be O of n. But because they're not nested in between each other, they run consecutively, so we would get something like, you know, n plus n, which might be 2n, but that is still order n. Okay, so this add method is going to be order n. The remove method, we have some some constant time statements, a conditional, an assert, an assignment, another conditional, and then we call remove gap. So let's go down and look at remove gap. Much like make room, remove gap has a loop, and in the worst case, we're going to be removing the gap at the beginning of the array. So we're again going to need to shift all the elements in our array. So here again, remove gap is going to be order n. Okay, so any method we call it from, which we called it from remove, is going to be at least order n. Now, all the other statements in remove look like constant time, just single statements. So remove, that makes remove order n, because the highest term that we have here is an order n method call. So adding is order n, remove is order n, getting the entry. So here's where we want to find the entry at a specific position. This involves what? Looking at the array at that position. This is going to be constant time. So getting the entry from AList is O of 1. Right, because there's no loops here. All we do is we get the array at that position. So this is fast. This is order 1, constant time. Determining whether an entry exists in the array. Here we have again a loop. This loop is dependent on the number of items in our list. So this is going to be O of n. So this contains method is going to be O of n. Okay, so we've got adding and removing O of n. Getting an entry is constant time O of 1. And contains is O of n. So let's look at the linked nodes implementation. Here for our add method, we have some constant time statements, and then we have a call to the private helper method get node at. So let's take a look at get node at. Get node at, again, involves a loop, and this loop might, in the worst case, iterate over the entire chain. So right, if we want to return a node that's located at this position, the worst case is that's going to be the last node in the chain, or that it's not even going to be in the chain, and we're going to have to look through the entire list to get there. So again, this private helper method is order of n. So any method that invokes it is going to be at least order of n. So when we go back up to our add method invokes get node at, so it's going to be order n. Okay. And then the rest of these are constant time statements, just updating the next references to things, and an increment. So this whole add method is going to be order n. So it's the same efficiency as the add method in the array-based version. They're both order n. Now let's look at remove. Our remove method has, again, some constant time statements. And then here we have another call to get node at. So this, again, is going to be order n. Okay, because here we have to, in the worst case, we have to loop through the whole chain to find the node reference that we're looking for. So this remove method, and the rest of these, the rest of these statements are constant time. So this remove method is going to be order of n. Again, that's the same as it was for the array-based version. So far the efficiencies are pretty similar to each other. Now, one note here about this code that I have here, that this is the same as get node at the given position. The reason that this line is written that we find the node before using given position -1 sent in to get node at, and then we find the node to remove by saying node before dot next, is that this is more efficient because it avoids the second call to get node at. So I had said in my notes here, that in my comment here, that this would give you the same functionality as invoking get node at given position, but this would require us to invoke get node at twice. Now note that if we did that, so if we had this as our code, the efficiency of the method would still be the same. It would still be order n, right? Because we have one order n statement followed by another order n statement, but these aren't nested, so that doesn't change the efficiency. It changes the running time basically from n to 2n, but both of those are order n. So this doesn't change the overall efficiency of our algorithm. It's still going to be order n, but in real running time, we want to avoid calling this multiple times, right? So using this construct here will not again change the efficiency, but it will make our algorithm in real time run slower. So that's why we use this way of doing it here, which allows us to just call get node at one time. Make sure that makes sense and post questions about that one to the discussion board. Okay, so that's our remove method. Next up, we have the get entry method. Get entry, again, we send in a position, and we want to know what element is at that position in the list. And here, for a linked chain, we have to, again, call this get node at, which we just said was order n. So get entry in AList was constant time. It was order 1, right? We could just return the element at that position. But in a linked list, in linked chains, in LList, it's order n. So it's less efficient to get an entry from the LList than from the AList. Our contains method also has a loop that in the worst case is going to loop over the entire chain. So that's also going to be order n, and that's going to be the same running time as with AList. Okay, so that's a comparison of the add, the remove, the get entry, and the contains methods. Now, one thing we could do to make LList a little bit more efficient is keep track of a tail pointer, and there's some discussion of that on the note, so take a look at that. And we're talking about worst cases here, but if we think about average cases, then the comparison of, average or best cases rather, and the comparison of AList and LList will change. Okay, so make sure you read about the details of that in the textbook and in the notes, and then post questions to the discussion board. One last method that I wanted to look at in these two classes is one that I added in the video, so it's not one that came with these methods, but in an earlier lecture notes, we added the get all less than method to both AList and LList. Okay, so with AList, we can see that what we do is we loop through our entire array, comparing each item and then adding it to the new list. Okay, so for this, this is going to be order of n, right, because we are looping over the entire list. And when we look at the LList implementation, we had said, I'd written this code here, that this way of implementing this would work, but that it was very inefficient. And hopefully now that makes sense of why. Because if what we do is if we loop over the entire chain, and then each time we're looping through the chain, we invoke get entry, well, remember the get entry is order of n. So this outer loop is order of n, and then nested inside of that outer loop is an inner statement that's also order of n. So that's going to lead us to this whole algorithm being O of n squared, which is bad. Right, so if we have this way where we repeatedly call get entry inside of a loop that goes over the entire chain, that puts this at a quadratic running time. And that's very bad. We don't want that. If instead we use this implementation where we just keep track of the nodes and we are able to just go through our loop, keeping track of the node and comparing each node that we look at, the data at each node that we look at, there's no nesting here, right? This is just a single loop that goes over the entire chain, but we don't have any other nested loops inside here, right? So this is going to be order n because it just involves a single loop. Whereas if we'd done this way, although this might be a little easier to understand, it's much, much less efficient. So this happens a lot, especially with linked nodes, is that if you have access to the actual node structure and you can use a temporary node to keep track and to chain through your elements one time, you can get code that's much more efficient than if you are repeatedly invoking some of the predefined methods, because those are going to lead to nested looping, which is very inefficient. Okay, so that's a review of the efficiencies of some of the bag and list methods. Again, please post questions about those to the discussion board.